Guarda, ti ringrazio perché è un argomento che mi interessa molto e su cui avevo anche riflettuto io personalmente. Quindi, dove l'ha pubblicato l'articolo, Carlo?
C'è stata un'intervista. Le risposte che ti ho detto a Blatto la fece subito o su Repubblica o sul Corriere, e gli altri ho letto la notizia sul mio cellulare, non so dove stia, ma si trova, sicuramente si trova. E francamente,
l'articolo di Rovelli è su YouTube?
Rovelli, se tu scrivi su Google Rovelli Fermi cattivo cittadino, cioè Rovelli in sostanza dice che Fermi è uno al quale del problema della bomba, dei problemi umani non si è posti. Nota bene che poi oltretutto anche gente che ha partecipato in questo poi prese le distanze, Oppenheimer, Szilard, quindi quello che è vero è che Fermi visse altri 8 anni, 9 anni dopo la bomba atomica, e in quegli 8-9 anni non ha mai detto niente, e questo non c'ha niente a che fare con la qualità di Fermi.
Sai, fra l'altro, Leo, chi è che prese una posizione molto critica? Era la sorella di Fermi. La sorella di Fermi gli ha fatto un commento dicendo che Dio ti possa perdonare, insomma. Senti, che faccio? Comincio?
Guarda, quindi questo tu mi stai dicendo, mostra che in realtà il problema è molto più complicato, e quello che ha detto Novelli non è una cosa scandalosa. Il problema è che c'è della gente che se tu dici qualcosa, se io dico che Amaldi da bambino rubò i cioccolatini al compagno di banco, non ho elementi per dirlo, ma questo non inficia chi è Amaldi. Non sto dicendo che Amaldi era un grassatore, però c'è gente che deve difendere il tutto di tutti gli aspetti di tutto.
Allora, scusa, allora che faccio? Comincio la presentazione?
Che ore sono?
Ok. Giorgio, could you please click on the height in the bottom box? There is, you have to click on height. Thank you.
Okay, but now I lost the presentation.
It shouldn't have.
Oh, can you see it now?
Yeah.
Dai, Giorgio.
Yeah.
Okay.
Oggi
I can see one.
Okay, thank you.
Okay, can I start?
Yeah, please. Thank you.
All right, great. So, first of all, where are we in the 3 days presentation? I'd like to remind you that we spent the first day reviewing properties of synchrotron radiation as the best source for implementing X-ray microscopy. Then yesterday we spent a lot of time looking at specific X-ray microscopy techniques. This was not a complete picture, but it allowed us, first of all, to discover imaging microscopy, that is radiology, and the role of the coherence, especially the spatial coherence of synchrotron radiation, which is very high, and it is a byproduct of having increased the brightness, because the brightness was increased by optimized and geometric parameters, making them small, and this also gave us coherence. So we spent a lot of time talking about coherence. The mechanism that is related to coherence is called in jargon phase contrast, and it means essentially that instead of using the intensity, that is the absorption, we are using the phase of the X-rays in phenomena like interference and diffraction and so on to produce the images. Then we spent some time talking about fluorescence, talking about different kinds of absorption microscopy, and talking about photoemission microscopy, and we introduced the notion of spectromicroscopy, that is the combination of microscopy and spectroscopy. Now, today, the program is going to be the following. First of all, we are going to complete that part of the discussion by talking about one last and extremely important class of techniques for microscopic investigations, that is those that are based on scattering of the X-rays, diffraction, and so on. So things that are once again related to the real part of the refractive index. Having completed that, I would like to spend a few minutes talking about one of the biggest X-ray microscopy programs ever, what we call Synapse, and this will allow us to touch also another aspect which is very important, the fact that right now we are producing incredibly large amounts of data, and this creates not only a technical problem, but also, if you will, a political problem. That is, we are thinking about a new approach, a new way to use synchrotron radiation sources, which could also be very relevant to the projects to develop new sources in South Central America and in Africa. The last part of my presentation will be dedicated to a new, very new and quite recent kind of X-ray synchronous radiation sources, which is the X-ray free electron lasers, or XFELs. And we are going once again to look at the basic mechanisms, the properties, and so on. And in this way, I hope to be able to show you once again that these things are not really very complicated. They are basic physics, and once you break the barrier or complicated formalism, they are quite easy to understand because of this their physical background. Then, in the end, we are going to see what are the characteristics of XFELs, and we are going to understand, I hope, that we are breaking new grounds by moving into unprecedented densities of electromagnetic energy, both in space and time. And the very, very, very last comment I will make is about the role of this new ground in basic physics. So let's start. And technically speaking, I will make the usual short break for questions in about 20 minutes. And we are going to have a coffee break of 5 minutes. And then we're going to have maybe a last break for questions. I will try not to exceed the total time, but I think that we can do it. All right. So what is the last class of microscopies that we must deal with? There are those that are related to the scattering of X-rays. Once again, the objects that are really interacting with X-rays are electrons. And so we would like to exploit this kind of interactions in order to understand what is the microscopic charge distribution of electrons in systems like molecules or solids, stuff like that, nanoparticles. Now, first of all, what is the background for this? Now, suppose that you take a X-ray beam and you get scattering from a small volume. Now, what happens is that the direction and the characteristics of the incoming X-rays are characterized in physics by what is called the K vector. The K vector basically is the momentum of the X-ray photons, and the direction, being a vector, is the direction of motion. You can see here that they're coming from this direction, and we are changing into this direction. Now, in a generic or general experiment of this class, we are going to put a detector somewhere around here, collect the X-rays, and try to retrieve from this result information about the electronic charge distribution. The theoretical background for that is very simple. Okay, it's at the same time, it's very simple, but very complicated to apply in practice. Why is it very simple? Because if you're looking at mathematics and the theory, you find that what if you call S the difference between the incoming and the outgoing K vector, then if you're looking at the dispersed wave, the scattered wave, okay, that is this X-rays here, as a function of S, the scattered wave is going to be proportional to this integral. Now, this integral should look very familiar because it's a function that we are trying to understand, that is the distribution of electrons in space, multiplied by this exponential, integrated over the entire space or the entire volume that we are exploring. Now, this is nothing but the Fourier transform of the F function. So basically, what we are measuring here experimentally is the Fourier transform of what we are trying to understand, what we are trying to analyze, the charge distribution of electrons. So you can have a simple idea, say that I'm taking the result, that is what I'm measuring, this wave, and then I'm going to apply an inverse Fourier transform, and in this way, we should be able to retrieve our charge distribution. Very simple. Well, yeah, very simple, but there are background problems. So let me, first of all, repeat what we are trying to do. So, first of all, we have a target that is a certain microscopic object. It could be a virus, for example. It could be a macromolecule or nanoparticle. We want to know what is the charge distribution on a microscopic scale. So we are going to send X-rays and detect those that are scattered using a suitable detector. Then once we get this signal here, we can try to invert the process, perform an inverse Fourier transform, and bam, you can see, let me repeat that, with a Fourier transform, we are getting the microscopic charge distribution. So it's very simple. However, as I mentioned, there are some background problems. The most important of this background problem is that in an experiment of this kind about scattering of X-rays, we are not really measuring waves. We are not measuring X-ray waves. The detector is not detecting the wave, that is the electric and magnetic field of the wave, is detecting the intensity. The intensity is basically the square of the wave, which means that all the information related to the phase, since it is in an exponential with an imaginary exponent, is going to be wiped out, because when you are performing the square of an imaginary exponential, then you get plus or minus the exponent, and the phase is getting out, which means that we cannot perform the inverse Fourier transform of the wave that is scattered. We can perform the inverse Fourier transform of the intensity of this wave. This creates all sorts of problems because it is not exactly the same thing. And so all the history of this kind of microscopic technique is marked by the progress in trying to understand how you solve what is called the phase problem. The phase problem has been plaguing this field from the very beginning, from its invention. Now, synchrotrons are quite good in order to solve these problems because, for example, they allow you to change the frequency of the X-rays and to take images at different frequencies. And there are rather complicated but very efficient methods in order to extract from this information about the phase. So by and large, with some difficulties, the phase problem can now be tackled. It's not automatically solved, but it is tackled. And it means that in spite of this fundamental problem, this class of techniques have been able to give us a number of very powerful experimental instruments. First of all, the scattering at big angles, large angle scattering, the small angle scattering, the scattering of powders, what is called crystallography, and then crystallography of proteins. It's a very complex field, so I don't have the ambition to look at all the details, of course, but I like to spend a few words in order to make you understand how actually you can use these techniques in practice and get very, very nice information about the microscopic charge distributions of important objects. So, first of all, let's look at the basic effect of the direct and inverse Fourier transform. So you can see that without going into the details, when you are looking at the shape of the object, you are getting some consequence about the scattering. So for example, if you are getting a molecule with two atoms, once you're performing the Fourier transform, you're getting something like this. So you can see that in the screen, you see something which is a fingerprint of the symmetry you find in the molecule. And this tells you that if you're looking without performing a full inverse Fourier transform analysis, but just looking at the figures of the scattered X-rays, you can already get an idea, a general idea of what you're talking about. So if you're now taking some kind of periodic system like a crystal, well, the crystal is periodic and the diffracted intensity is also going to be periodic. Same thing for this other kind of periodicity. So by and large, if you look at the periodicity of the diffracted X-rays, the scattered X-rays, this gives you immediately an idea of the periodicity and the symmetry of the original system. And this is, by the way, what is creating what is called the Bragg spots. So that is this kind of bright spots in the screen. Okay, so much for symmetries. But now let me go to these two different techniques, that is small angle scattering and large angle scattering, because they are important in practice in order to implement the analysis of the microscopic structure in the most effective way. Okay, it is, you don't want to start with nuclear weapons. So if you want to understand a microscopic structure, you want to be reasonable and start step by step. Okay, so for example, in the case of the COVID structure, people did not start immediately looking at the full details, the position of the atoms, and so on. First of all, they got a general idea of what was the shape and what kind of class of viruses we were talking about, and so on. And then they went into the details. How can you do that? Well, when they are performing an experiment of scattering, you're not really getting all the scattered X-rays, because your detector is going to be of limited size. So all these scattered X-rays, you're only going to get a small portion. This is what is called the small angle scattering. Now, after you do that, then you can try to improve the situation by using a larger area detector. So you go for large angle scattering, a more complete picture. What is the difference between this and this? Well, of course, you understand that the information that you're getting from a small angle scattering experiment is going to be more limited than the information you get from a large angle scattering experiment. And this is immediately reflected in the properties of the Fourier transform. In fact, if you're looking at what you get, once you perform the inverse Fourier scattering of a small angle detector, you're only going to get the generic shape, microscopic shape of the object, the microscopic charge distribution. You do not see it in detail. In order to see the details, you must go for larger angles. So this is telling you immediately what can be a good and effective strategy that is not wasting resources unnecessarily. When you start looking at something new and you don't have any idea what's going on, you first start with small angle scattering. You're getting the general shape, and then you can focus and start to refine and refine and refine. Of course, taking a scattering at large angles means that you're getting a truckload of data, so you must process them. In a typical analysis of this kind, people are spending maybe 1 hour to get to the results, the experimental results, and then they spend days or months in order to process these results. So this is a step-by-step process, which, as I mentioned, was indeed used in the case of COVID, the COVID virus. Now, before leaving this topic, I would like to talk about this specific technique that is the macromolecular crystallography. All right. This is right now a gigantic enterprise because it's the most effective way we have in order to explore macromolecules like proteins, parts of viruses, and stuff like that. So we would like to understand what is the atomic structure of these molecules. But however effective and powerful these techniques are, we are still facing a big problem. The big problem is that X-ray photons, since the wavelength is very short, the photon energy is very big. H nu, the energy of a photon, is also very big. And so if you are shooting a single molecule with an X-ray photon, there is a chance that you are damaging or destroying the molecule. And so it is not completely easy to avoid the problems of damage done to the sample by the process of taking data. So we would like to solve this problem. How can this problem be solved? Well, instead of looking at one single macromolecule, you can try to obtain what is called a micromolecular crystal, which is a crystal in which, instead of having the atoms of a normal crystal, the components are macromolecules. And so you are organizing the macromolecules in a periodic ordered array. And then you perform the scattering experiments, not on a single molecule, but on this collection of molecules. They are periodic, and so the molecules are going to give contributions that ideally should just be the same contribution over and over and over with this periodicity. And so the information from one single molecule should be reinforced by the information of all the other molecules. Of course, in this process, some of the molecules are going to be damaged. However, if you have a crystal that is big enough, there are enough macromolecules that are not damaged. And so in this way, you're still getting a good signal. And therefore, in order to perform this kind of experiments, at the present time, for example, to find the structure of a new protein, you must create a crystal. This is the biggest challenge of the entire process, because getting crystals is difficult, getting crystals of reasonable size is even more difficult. It takes a lot of time. It takes a lot of trying and experimenting methods. The methods are different for each kind of macromolecules. So getting results is a big challenge. It's the biggest challenge in this entire procedure. This has a number of consequences. So, for example, when you're trying to find a new drug, okay, in order to attack some kind of micro object, okay, micromolecule, a macromolecule, then in order to find the right drugs today, what you are doing is trying to develop microscopic things that simulate the structure of the object you want to attack and perhaps kill. And in order to do that, you must understand what is the structure of the thing you want to attack, and also what is the structure of the things that you want to use, the weapons you want to use to attack. However, this means that for each potential drug molecule, you must explore the structure. And this is done, but it is done in a painful way, because for each one of the possible candidates for drugs, you must first of all start getting crystals, then increase the size of crystals until you get the crystals that are good enough, big enough to perform the analysis. And this takes a lot of time. Once you look in a typical process to find a new drug in the pharmaceutical industry, the time lapse between the beginning of the process and putting the drug in the market is about 10 years. 10 years, I mean, this is spent essentially a lot of time in finding structure. That is, in throwing out a number of promising microstructures after solving them and so on. And in order to find the microstructure, you need to develop crystals. Then after this, you need to test on different kinds of specimens, starting from animals, then going to humans. And finally, you do the marketing and you put things in the market. So 10 years is a ton of money. Is a lot of money. It is why drugs, the sophisticated drugs, are so expensive, because there is a lot of research work going on. So of course, it would be nice if we could avoid this step of developing crystals that is taking a good portion of this process, a good portion of the time for this process. It would be good, but we're not there yet. And so we still had to cope with crystallography and producing crystals, which is something that takes a lot of scientists, or colleagues, a lot of time, a lot of efforts, and so on. We shall see later what is the dream, but let me not anticipate that. The dream is to go back to the idea of getting structures from single macromolecules, but we are not there yet. And so right now, crystallography is a necessary thing. Keep in mind that the amount, the number of objects that we must solve, for example, the number of proteins we must study from the structural point of view, is absolutely huge. The data bank for that is one of the biggest collections of data in the world. And we are still a very small fraction of the total path, because we are just looking at a fraction of the interesting proteins in nature, or interesting macromolecules in nature. So there is a lot of work to be done in the future that is going on. Also keep in mind that this difficulty in getting crystals is not equal for all the macromolecules. For example, the macromolecules that are in the membranes of physiological system, which in some cases are the most interesting kind of macromolecules, these are hydrophobic, and the process of creating crystal is typically something of wet chemistry. You need water. So the two things are going against each other, and that's one reason for, if you're looking at the data bank, you find that there is a huge amount of proteins already, but they are only in certain classes. So that's the challenge that we are facing in the case of X-ray crystallography. And of course, synchrotrons are playing an extremely important role because basically, because of their intensity, they allow you to use smaller crystals to start solving structures at an earlier stage without waiting for big crystals. And this, once again, is exactly what happened in the early days of the COVID fight. All right. So now we are ready to go to the Synapse project, but I'd like to spend a very few minutes talking about one of the biggest technical problems that we are facing in X-ray microscopy. Big technical problem is how you focus X-rays, because many of the techniques we've been talking about reach lateral resolution, spatial resolution, basically by taking X-rays and focusing them. So, question is, how can you focus an X-ray beam? Once again, it's not easy. It's not easy, and this is one of the biggest technical problems. It's not easy, primarily because if we are trying to use the same devices that are good for focusing, for example, visible light, they're not working. So suppose you take, for example, a normal lens that is very effective in focusing visible light. This is based on refraction, and is not going to be working for X-rays for a couple of reasons. Reason number one is that the refractive index for X-rays is always extremely close to unity, so the effects are really evanescent. In a broad sense, what we've been seeing about phase contrast is related to this fact. Second is that X-rays are typically not transmitted but absorbed by solids. So if you try to get them through a lens, you're not going anywhere, all right? The lens is going to absorb your X-rays. So can you use mirrors? Because the other way to do focusing for visible light is to take a mirror. It's very nice, but it doesn't work for X-rays either. The reason is because, as we shall see a little bit later, there are no good mirrors for X-rays, except when we are working at extreme grazing incidents. It is the angles that are close to perpendicular, they are not just, they're not going to give you any reflection. So you don't have mirrors for X-rays, and therefore you don't have focusing mirrors. So is this a hopeless situation? No, okay, that is during years of technological evolution, there's been a lot of progress, and now we can count on a number of devices that are not easy to produce. They are not easy to use either, but they work. Let me just give you a few examples. Number one, of course, instead of taking the mirrors that you use to focus visible light that are working at the near normal or near perpendicular incidents, you can work with grazing incidents, as we can see here. Now, you realize that since here we have a beam with an extremely short wavelength, that means that any kind of defect in a mirror can have tragic consequences of the result. And so preparing one of these mirrors is a fantastic technological challenge. You must get to surfaces that have an accuracy that is beyond description on a microscopic scale. And the accuracy is not only related to the roughness or the residual roughness of the surface, is also related to the curvature. So possible, very difficult, exceedingly expensive, but you find this kind of mirrors everywhere in the synchrotron radiation facilities. Solution number two, it is what is called the Fresnel zone plates. The Fresnel zone plates for visible light are objects that we see every day. For example, if you're looking at the traffic light, you realize that in many cases the traffic light is using Fresnel zone plates. What is a Fresnel zone plate? Well, as you probably know, is a series of circular zones. Then you go from an absorbing zone to a transmitting zone to an absorbing zone and so on. And when you're looking at what happens to an X-ray beam that is coming here, which is not focused, then you realize that there is constructive interference of the X-rays that are passing through the transmitting zones. And because of the periodicity of these zones, then you're going to get the constructive interference that gives you focusing in a specific spot. So this is possible, but by and large, the periodicity of the zones is related to the wavelength. And so you can actually go to a novelty store and buy a Fresnel zone plate for visible light, and it costs you a couple of dollars or pesos or whatever. It is very inexpensive, very easy to make. You find something like that in banknotes and stuff like that. When you're trying to do the same thing for X-rays, then you're talking about doing things on a scale of the wavelength of X-rays, which means angstroms. So if you're looking at these objects, fabricating them is once again a fantastic technological problem. It is done, but you can imagine that you must have an object with this delicate structure with an aspect ratio, that is, the zones that are absorbing must be thick enough in order to absorb X-rays. So it cannot be extremely thin. You must have thick zones that are separated by an exceedingly small distance. So in the early days, producing these objects was a nightmare. Right now, you buy them. You buy them from specialized people that are producing them. And believe me, they are not inexpensive, but you can buy them. Before concluding, this is another class of focusing devices for X-rays. They are the so-called Schwarzschild objectives. Now, the Schwarzschild objectives, for people that know about astrophysics, they are related to what is called a Cassegrain objective for far stars. Basically, it's the combination of a convex mirror and a concave mirror. X-rays are coming here, they are coming through a pinhole, so they are producing this kind of beam, which is not focused at all. There is a reflection here, and there is a second reflection, and you get, excuse me, oops. Okay, you have a second reflection that produces the focusing. Now, you may actually object that this makes no sense, because I've been arguing a few minutes ago that we are not getting X-rays, X-ray mirrors, except a very grazing incidents like it happened here. And so how can you handle these kind of reflections that are not really grazing incidents? You need an additional ingredient. An additional ingredient is multi-layer coatings. That is coatings with materials that are reflecting, that are absorbing or reflecting X-rays, but they are periodic. And so because of the periodicity, they can reinforce the reflection. And once again, this can be implemented, but it is not an easy kind of technology. So much about focusing X-rays. And now let me go in the last minutes before the coffee break to synapse. I want you to look at this movie. Here we are navigating in the brain of a rat. And here you see a picture of the brain, okay? So as we have seen in one of the images I showed you yesterday, we can detect not only the cells, but the connections. Now, if you are looking at something like this, and allow me to repeat this, okay? Oops. Yeah. Ok?
Giorgio, si è interrotto, Se puoi tornare indietro dall'inizio di questa trasparenza, per piacere.
Ok? All right? Scusa che lo devo ripetere. All right. There it is.
Yeah.
Can you see it?
Yeah.
Great. Folks, when I started seeing things of this kind, to me, it was an emotional experience, because here we are seeing, perhaps for the first time in history, what is the complexity of the systems that we are using to think, to be alive, to perform functions, and so on and so forth. And keep in mind that in this image, we are not showing the entire network. We are showing a portion of the network, because to make the neurons and connection visible, we have to use staining. And the staining is only showing you a small portion of the entire brain. So the entire brain is even more complicated than that. We are seeing the most complicated and the most fantastic object in nature, by far. It's absolutely fascinating. How can a system so complicated work? And for example, allow me to speak now to you and give this lecture. This is something that defies imagination, but also is, to me, the biggest challenge that the science and technology is facing at the present time. And so when we started to realize that it is now possible to look at individual cells and look at their connections, when we started scratching our head and think, what can we do with that? And there was a guy, the name is Yu Quan Wu, and he came with a very ambitious idea. That is, why don't we stop playing with Drosophila, with insects, with mice, and so on? Why don't we go straight to the human brain? Because this is really what we want to do. Okay, so we must go from the rat brains, which is the bulk of the experiments at the present time, to the human brain. And we want to be able to perform the task in a reasonable amount of time. And so for this, there was a collaboration that was created. It's called Synapse, that stands for synchrotrons for neuroscience. Excuse me, I need to stop my phone. Okay. Synchrotrons for neuroscience and Asia Pacific strategic enterprise. So this is a collection of many different synchrotrons. Most of them are located in the Far East, in Korea, in China, in Japan, in Taiwan, in Singapore, in Thailand, but also we have facilities in Australia and in Jordan. Okay, and more are coming. Now, so we are trying to work in parallel with this entire consortium, and our super ambitious goal is to have a map of the human brain in a reasonable number of years. What is a map? It means that we are going to map all the connections of the cells in a human brain. We are working with fantastic colleagues in neurobiology, and so we are, of course, asking them, does this make sense? Are we providing an important kind of information? And the answer now is yes. This could be a turning point for the big struggle in order to understand the working mechanism and diseases of the human brain. So, obvious question is, why do we need this kind of approach? Why do we need this big collaboration? The basic reason is the amount of data we are dealing with. It's very simple. If you are trying to understand how big is the data set for a single human brain, we are talking about 1 exabyte, which is 10 to the 18 bytes or 10 to the 9 terabytes. So you need essentially 1 billion of your small plug-in memories in order to get the data for images for a single human brain. Of course, mapping a human brain is our first objective, and it is very nice. We'll be very happy when this is completed, but it is not sufficient, because in order to really have a meaningful study, you need to study several brains. We are estimating about 100. Okay. Paradoxically, the smallest problem is to get enough brains, because all the neurobiologists that die, they donate their brain to science. Okay, so there is plenty of brains around. But the problem is the amount of data, because we're talking now about 100 exabytes. Now, if you try to make an estimate by comparing this with Google, the total capacity of Google is a well-kept secret, but we believe that this is equivalent to 10 times the absolutely total capacity of Google. And so we are talking about a huge, huge amount of data, which creates very practical problems. First challenge, tagging data. Because if you're using a single synchron radiation facility and you're working in series, then it would take several years in order to complete a single brain, and of course, centuries to complete the entire study. Folks, I'm not personally so much interested in a study that is going to end 2 or 3 centuries from now. Okay, and so we wanted to find a way in order to shorten the process, and the way is to ask several facilities to work in parallel and to take data in 10 or 20 different facilities, which is going to divide by the total time by a factor of 20 and reduce the century into a period of 5 years. That's the reason for Synapse. And the other one is that we also need to have enough resources in order to handle this huge amount of data. Because of this, in Synapse, there are not only synchrotrons, but also supercomputing center like NSCC in Singapore. And they are developing new software, new storage, and so on in order to handle the process. So much about Synapse. And I think this is a good time to stop here. So I will entertaining a few questions if there are questions, and then I'm going to propose to take the usual 5 minutes coffee break. Questions, please.
Giorgio, I have just one doubt. When one makes something like that, collecting data just in one place, suppose that in Singapore there is an earthquake, the supercomputer disappears. This information will be lost. Are there a way of, I mean, a backup of a computer is easy. My question is, how feasible are the backups of this order of magnitude the big computer?
Thank you very much, Leo. I think this is a very interesting question. It is one of the big problems, because of course, when talking about data handling, it's not only processing data, processing images, and so on, but it's also storing the data and making this stored data available to every scientist in the world. We don't want to have any barriers. Any scientist in the world, wherever is the location, should be able to approach that. Now, one important portion is, of course, the security of the storage, which means that we need a huge amount of memory. Right now, we are trained to think that memory is no longer a problem, because you buy a laptop computer and you easily get 1 terabyte. Here we are talking about something which is much, much bigger terabyte. And so the memory is a problem. So we need the multiple storage. Also, we need to have ways to allow people to access the information. So, not easy.
Okay.
Other-
There is another question in the call. Online. Somebody, quien tiene la mano alzada, simplemente por favor abra el micrófono y hace la pregunta. Y en el chat, there is 2 questions in the chat, Giorgio.
Yeah, I'm going into the chat. Excuse me.
Hola, buenos días, ¿me escuchan?
Sí, adelante.
Sí.
Muchas gracias. No voy a hacer la pregunta en inglés, pero pues la voy a hacer en español si de pronto alguien me ayuda con la traducción. ¿Cuánto es el valor económico de estudiar el cerebro a ese nivel que lo presenta el profe durante su exposición?
Ahora, el valor económico es muy difícil, pero es muy grande. Porque cuando hablamos del mecanismo del cerebro humano, hablamos del mecanismo sin problemas y del mecanismo con problemas. Allora, si se podría determinar fármacos para los grandes problemas sociales, como la esquizofrenia. El impacto financiero es enorme. So we are not. Let me complete in English because I don't want to make any misunderstanding. The financial impact of solving even one of the smallest problems in the brain function would be huge, because right now these kind of problems, the illnesses that are coming from malfunction of the brain, are impacting a huge portion of humanity with tremendous consequences. So there is no question that the results are going to be very valuable. Of course, we are not offering the solution for everything. We are offering a piece of the entire information. There are many important projects in parallel that are attacking the same problems from different points of view. Like, for example, I'm in Lausanne, and here in Lausanne, we have been the headquarters of the Blue Brain project that uses computer simulation and more conventional kind of experimental system. I'm convinced that in the next several years, we are going to have a revolution in the understanding of how the brain works and also how the brain does not work. And so you understand that the financial problems or the financial consequences are huge. Espero que me has entendido.
Más o menos. Okay, doctor, thank you very much.
Oh, Giorgio, I would like to add another argument which I think could make sense. There are many sickness which are typical sickness which have to do with the functioning of the brain. So if you think, for example, on all the problem of studying the dementia of the people and so on, I imagine that if this type of things, I don't know, and please confirm if this is true, that this can also shed light on problems like the Alzheimer and things like that. Am I wrong or not?
Yes, you're absolutely right. For example, Alzheimer is a typical case that is becoming more and more popular because people are living for a longer period of times. They do not die of cancer or heart attacks, and so they are more exposed to Alzheimer in the long run. But take things like Parkinson or whatever kind of social disease that is coming from the brain. We don't understand anything, okay, or very little. We are using drugs in an almost blind way. If you could be more specific, that would be great. Okay, I'm trying to see the questions in the chat.
Giorgio,
Yep.
I would like to make another comment in this direction, in this sense, that to some extent, I think that what you are doing is very similar to when people decided to study the human genome, basically.
Yeah.
Now, once one understands how the brain works, you can also think that you can take people who have died having an Alzheimer, having a Parkinson or so, and study those brains, and perhaps you can find things which can, again, shed light for how to approach this type of sicknesses with a process which is not the process of medicines or things like that. I'm perhaps I'm talking about a very far future, but certainly the understanding of the brain is the first step to understanding also the brains which for some reason are not working properly.
That's exactly the point that I was trying to make before. It is, but let's not forget we are not there yet. That is, we are still just starting to look at things with the right instruments. And so, of course, in the second stage, the target would be illnesses. But we are still in the first steps in which we are only now we are able to see the connection. So it is going to take some time, unfortunately. No, unfortunately. Okay, I'm trying to find the questions in the chat, but there is a long text here, and so I'm wondering if you could read the question to me.
I can read for you. Meanwhile, there is another hand raised. So Heidi, adelante.
Hello. Firstly, thanks for your excellent talks. And then I apologize for my poor English, but the question is, firstly, the part of the talk, you talk about the meter radiation. And my question is, can the meter radiation that doesn't arrive of detector affect another components of the systems? That is the radiation outside of the, for example, solid emission angle. How do you control the rest emission or the radiation emitted out that damage the system? Maybe you understand me, the question?
Maybe, but let me try to see if I did understand you. So your question is how you handle the radiation that is not detected, but it goes somewhere else. Okay, now all these systems are basically in closed chamber, most of them under vacuum or ultra high vacuum. So there will be walls that are absorbing the X-rays. And so that's not really a problem. Okay, there's never been in the history of synchronous radiation a problem with leaks of X-rays, and there has been historically only one accident many years ago. But the entire operation is quite safe from the point of view of handling X-rays. I hope I did not misinterpret your question.
Okay. And another question is, I understood that the difference between another techniques without using the synchrotron source is the quality of the radiation. Yes, is this radiation is more better than another source.
Okay.
And what is the difference?
Yep, go ahead.
What is the difference if I use I don't know, another technique like XPEs or whatever technique, and the difference or the another technique that we can use with the cyclotron. I understand that is for the quality of the radiation, maybe?
All right, let me just make a couple of general comments. First of all, I think that we should not fall in the trap of advertising. Okay, that means synchronous radiation is wonderful, the techniques are wonderful, but they are not the only experimental techniques around. And a sensible way to approach a problem in this time is to use all the techniques that could give contributions. Now, in this general picture, there are other things like, for example, electron-based techniques, okay, because you can get electrons with the short wavelengths necessary for the study of chemical bonds and so on. There are some specific advantages of X-rays. We mentioned this background characteristic of having wavelength and photon energies that are commensurate with the size of chemical bonds. There is also the fact that photons don't have a mass, and so by and large they are less damaging or interacting with the system. But once again, there is a spectrum of techniques, and I think that a good scientist should just look at all those that are available and make all the necessary choices. Okay, I would propose to take a 2 or 3 minutes break, okay, if that's okay, and we'll start as soon as possible. All right?
Okay. There is another question, but you know.
Alle 11:10. Alle 11:10. Alle 11:10. La sono 10.
Do you want to answer the question now or after the coffee break?
Let me take a very, very short coffee break because I need some water, okay? And so we'll start in 2 minutes, so it's not a coffee break.
Okay, okay, okay. ¿Hay café? Si quieres tomar café. Eliana, ahora atendemos tu pregunta también. Quedan 2 preguntas pendientes.
No, profe, fue que metí mal el dedo, perdón.
Okay. ¿Tienes la ruta? Favorito. ¿Quieres galletas? No, sí, está bien.
Okay, here I am.
Okay, the first question is from David.
Okay.
David Julian says, is there some difference between collimated light and focused light? Because I remembered that in the first class you told us we can take advantage of the cyclotron because the light of the X-rays are collimated.
Yeah. The 2 terms are not equivalent because when you are doing the focusing, for example, you take visible light, you can get a big source, and then you are concentrating the source in a focal point. So the angles can be also pretty large if you start from a big source. Instead, collimated means that the beam at a small angular range from the very beginning. So they are not 2 terms that are equivalent. Okay, let me suggest that at this point, we're going into the second part of the presentation, since I'm starting to be concerned about timing. I have until, I have another half an hour, right?
Yeah.
Good.
Right.
So, and I will entertain questions. I am on a time limit after the end of the talk, but let me go into the talk. And I hope that you see now the presentation. And as I mentioned, I would like to talk a little bit about this new class of X-ray sources, the X-ray free electron lasers. Now, in order to introduce the argument, let me start by saying that if you're looking at the properties of synchronous radiation from a storage ring, then you realize that many of these properties are reminiscent of those of a laser. There is collimation, there is intensity, there is brightness, and there is coherence. So you may wonder, but are we talking about lasers? Are these X-ray lasers? The answer is no. Because if you're looking at what is a laser, then you find that if you take a visible or infrared laser, like a laser pointer, well, you must have some kind of optical amplification. You must have a system with two mirrors that are producing an optical cavity, so the photons are going back and forth. This increases the path, increases the optical amplification, and so on and so on and so on. Now, you do not see these kind of things in a storage ring. So, although the properties are reminiscent, the source is not a laser. However, there is now this new class that I just mentioned, that is the X-ray free electron lasers. And in this case, we do get a laser-like mechanism. And by this, I mean that we are getting an optical amplification of the emission. In order to understand what's going on, we must take into account an element that so far we did not include in our presentation. That is the fact that, as we already mentioned, the electrons are not traveling alone in the accelerator, but they are traveling in bunches. And so, suppose now that we take a very long undulator. We'll see later why we need a long undulator. And now we get an electron bunch. The electron bunch with many electrons enters the undulator, and of course, there is the interaction, and the electrons start emitting radiation. Suppose that one electron emits a wave. Then, in the following, the electrons, the bunch of electrons and the wave are traveling together, and this is what happens. One can demonstrate that because of the interaction, the electrons start becoming rearranged on a microscopic scale, producing very thin slices with a period of one wavelength. So now the emission is not from all the electrons in the previous bunch, but is from organized electrons. And let's see what happens. That's the emission. You see what happens? That the difference, the emissions from different micro bunches are reinforcing each other, so they are producing optical amplification. That's a basic idea of a free electron laser, but of course we have a lot of questions to be tackled and answered. The question number one is, what is that really pushes the electrons to form these micro bunches? These are what we call, with a very complicated term, ponderomotive forces. That's fuerzas ponderomotrices. And they are complicated. They are complicated things that are created by the interaction between the electrons, the wave that is emitted, and the undulator. So there are three different actors and so on. You can understand that if you are trying to write all the equations, it can become very complicated. But I like to argue with you that the essential points can be understood in very simple terms. First of all, this is the wave. You can see that the wave has fields, and it has nodes, okay, these points in which the wave is zero. So no matter how complicated is the wave, we know that when the wave is zero, the forces are zero. And therefore, if you are regrouping electrons, these nodes, that is the 0 points of the waves, are where the electrons could accumulate. So this is the first realization. It's very simple, but we have to be careful, because the fields, the electric fields and the magnetic field of a wave are going in different directions, and of course, this is creating forces in different directions. So if you want to look at the realistic picture, you find a situation like this, with two kinds of possibilities. In this case, the forces are pushing the electrons to the node. In this case, they are pushing electrons away from the nodes. So here, what you see is that there is accumulation, not in all nodes, but in every other node. And that is why you get the periodicity of one wavelength. It's as simple as that. So you don't need to go into the details of the ponderomodic forces. You just need to look at this very simple argument to understand that you must have an accumulation of electrons with a periodicity of one wavelength. Now, you may start wondering at this point why, if you are going around the storage ring, a generic storage ring in the world, and you're looking at an ondulator, why the ondulator is not operating like an X-FEL. I mean, in most cases, we do not see an X-FEL mechanism. The reason, actually, there are two reasons, and they are quite subtle. Number one, if you're looking at relativity, then you realize that the mass of the electron must be changed, and it changes not only with the energy of the electron, but also with the direction of the electron. So there is a thing that is called the longitudinal mass, okay, which is the mass for motions in the longitudinal direction, the direction of motion of the relativistic motion of the electron. And this relativistic mass is m0, the self-mass of the electron, multiplied by gamma to the third power, gamma cube. Now, gamma is big, gamma cube is very big, gamma cube m0 is something which is no longer the very light mass of the electron, but something which is much heavier. Our electrons are like small stones, and so moving them around it can be done by the ponderomodic forces, but the motion is pretty slow, and it takes some time in order to accumulate the electrons in the microstructure. So that is why you need a very long ondulator, because otherwise there is not enough time in order to complete the process and move the electrons in the longitudinal direction so they can accumulate. But there is another reason. The reason is that if you're looking at the structure you're getting, you realize that now this is another picture of a microstructured electron bunch. The period is one wavelength. One wavelength, we are talking about the small wavelengths of X-rays. So it's a very, very delicate structure with microscopic features. Now we are living in a real world, and so all the systems here, the magnets, the electron beam, and so on, they have defects, they have imperfections, and so on. So you need to struggle in order to get an absolutely perfect system and to avoid simply to destroy your microscopic organization of the electrons. So this can be done, but it took a long time in order to do that. And in particular, there is a funny history that is the FELs, that is the free electron laser, were invented many decades ago, and infrared FELs were ready and working something like 40 years before the X-FELs. And the reason essentially is this one. It is, if you're looking at the infrared, the wavelengths are very long, the structures are not so delicate, and so you can be more tolerant you're looking at X-rays, is a fantastic kind of challenge, which was launched by a colleague in UCLA, Claudio Pellegrini, who is essentially the father of X-ray free electron lasers. Now, this is a general picture of the scheme of an X-rail. There is some kind of accelerator. In most cases, we are using linear accelerators rather than storage rings. The linear is sending an electron beam into the very long ondulator, and the electron beam progressively is micro-shaped and starts emitting photons that are going to essentially the same micro-shape of the electron beam. Now, there is another important point to realize, that is, we cannot use an optical cavity as we do for optical or visible lasers, okay, because there are no mirrors for X-rays. And so we must find some other kind of solution, and this basically, it is what is called in laser technology super radiance, meaning that there must be enough optical amplification, not by bouncing the photons back and forth, but in a single pass. The entire thing must work in a single pass, which means that we must really have a very strong optical amplification, which means we must have a density of electrons in the micro bunches that is extremely high, okay? And so this dictates a number of conditions for realizing in practice an X-ray free electron laser. We must realize optical amplification in a single pass. Consequences of this. If you're looking now at an X-ray pulse from an X-ray free electron laser, this is a reflection of the structure of the electron bunch, okay? And we must have a high density of electrons to increase the optical amplification, which means that the size of the bunch must be small. The duration of the corresponding photon pulse is going to be given by the size divided by the speed, which is almost the speed of light. And so the size is small. This is a short time. We are talking about pulses that are in the order of femtoseconds or less. So these are femtosecond pulses of X-rays. Now, compared to the time structure we got from accelerators like storage rings, we are getting into a completely new ultra-short domain. Furthermore, in order to have the high density for high optical amplification, we need to have a very small cross-section. So the small cross-section is going to give us very high brightness. So we are concentrating a lot of electromagnetic energy in a short pulse and in a compact pulse. We can go to another aspect. This is just to show you that you can actually develop theories of the X-ray free electron lasers that are very simple. I don't want to spend too much time on this. It's quite easy, but I want to go to the important next point. So this is a calculation of how you can estimate what happens to the intensity of the wave as there is the interaction with respect to the electron bunch and to the ondulator. So you can derive the simple equation, and the solution for the increase in intensity as a function of time, or if you will, of the distance, is going to be the solution of this equation, which is an exponential function. So you predict that there's going to be an exponential increase in the intensity of your bunch of photons. Now, this is actually what happens. This is confirmed by experiments, but it is not going on forever. At a certain point, there is a saturation of the effect, and so after a certain time or a certain distance, the increase is no longer going on. Why so? Well, there are a number of issues. Let's now have another look at the situation. Now we are looking from the point of view of the electron bunch. So let me send the electron bunch in the ondulator. We start emitting radiation. there it is. There is the interaction, and we see what happens to the microstructuring. Let me repeat that, because I want you to notice something which maybe you did not notice before, which is, let me do it once again, all right? The fact that the micro bunching is complete much before the end of the undulator. And once we get a situation like this, then the increase in intensity is no longer going on at the same same speed as before, and so we are going into saturation. Furthermore, since the electrons are losing energy by giving energy to the wave and amplifying the wave, their gamma is changing, the emitter wavelength is changing, so they're not contributing anymore to the initial wavelength. So all these and other factors are causing the saturation. At any rate, we could not imagine to go on forever with this increase in intensity, because we have limited energy we can put into the system. So at a certain point, it must saturate. Now, let me now tackle the issue of coherence, okay? Because coherence has been a problem for X-ray free electron lasers. More specifically, we must distinguish once again between space coherence and time coherence. And we can see that the space coherence is excellent, because we have seen that the electron bunch is very small, so the area is very small and so on. However, time coherence has problems. Why so? Well, let's look at what happens in the mechanism of emission. You've seen that basically the undulator is amplifying the initial emission of photons as they're getting into the undulator. Now, the emission of photons is a stochastic process. That means it happens at random, and therefore, what we are getting, I'm sorry here, I lost once again the color of the letters, but that is basically, since it is a random process, we cannot guarantee to have the same pulse line shape from one pulse to another, to another, to another. Each pulse is going to have a certain structuring time, and the different structuring time means, according to the Fourier theorem, that we are going to have a broad range of wavelengths. So intrinsically, in X-ray free electron laser, based on this mechanism of self-amplified spontaneous emission, or SASI, is not something that has a high time coherence. This is not very good, because we would like to have experiments in which we can exploit the time coherence. And so people in the field have been struggling with these technical problems for many years. And finally, they got to the solution, which is what is called seeding, sembrar. So instead of amplifying the random emission of electrons as they enter the undulator, what we are doing is to take the undulator, but use it in order to amplify a wave that is produced by another source, okay? And the other source can be controlled, and you can get a completely coherent wave. So once again, let me show. The external source is injecting in the undulator a coherent wave, and then the coherent wave is amplified, and we are getting something which is clean with high time coherence. This is not an easy technology. In fact, until about 5 years or 6 years ago, it was considered by some of the best experts in the field as impossible. But actually, it is possible. And there are cases, we'll see one in a moment, in which we are getting indeed high coherence thanks to the seeding procedure. So, for example, if you are looking at the entire picture of Electra, we have seen what happens in the large circular building, but you may notice that on the sides, there is also this very, very long structure. And the very long structure contains a X-ray free electron laser, which is called Fermi, free electron laser for multidisciplinary investigations. This is a working machine. It is a seeded free electron laser, and it is one of the best X-ray sources around everywhere in the world. But there are now a few other examples. So this is now a real technique, not just a distant dream. We're almost getting to the end of my presentation, but I need to tackle still a couple of questions. Number one, it's very nice to have a free electron laser producing these fantastic pulses. We are talking about pulses that have a duration of femtoseconds and pack up a power of the order of gigawatts. Well, these are beasts, okay? So how can we use them? Because if you take a small system like a molecule or a nanoparticle, well, what happens is that the damn thing explodes, okay? Now, I must admit that it would be a bit difficult to go to politicians and ask them to fund a very expensive machine in order to destroy the system that they want to study. And so we need to really understand what we can do with the X-ray free electron lasers. It's not just a matter of increasing the power or the intensity or the brightness. We are getting into a completely new field. Now, the point which is very important and it could be the key to the future is the fact that the pulses of X-rays are very short pulses, order of magnitude femtoseconds. Now, what is the time of an explosion like this? God knows, because this is a field that we have not been exploring yet, but there are calculations, there are simulations, and they seem to agree that the scale is also of femtoseconds. And so people are starting with the idea that you can actually take data dynamically, look at the structure during the explosion, then reverse time using a computer and try to retrieve the structural information at the beginning of the explosion. This is one possible answer to the challenge of crystallography, because in this case, you can say, well, I'm not trying to prepare a crystal, which is something difficult. If I cannot prepare a crystal, I can still try to understand the structure of a single micro object by accepting the distraction, but looking at things as a function of time on a scale of femtoseconds, and then inverting the thing and trying to retrieve, extrapolate what was the instant structure. Is this possible? It has been proved for some pilot system. It is very far from being an easy thing. We still do not know how far this technique can go, but it is certainly one of the avenues that is being explored right now. In more general terms, once you're talking about the applications of free electron lasers, we are talking about essentially super short phenomena. So this is a set of examples of things that are happening on a scale that can be explored using the ultra short pulses of X-ray free electron lasers. Folks, we are opening up a completely new world of research, opening up a time domain that has been very scarcely explored with other techniques. And so, once again, the sky is the limit, and we are getting a lot of new opportunities. So this is for applications in physics, chemistry, material science, and so on. But, as I already mentioned several times, there is something intriguing. It is we are, once again, we are packing with a seeded free electron laser X-ray field. We are packing a lot of energy in a small volume and in a very short time. And so we are touching something that is new in fundamental physics. Let me ask you a challenging question. We know that in physics, in quantum mechanics, the way nature of objects plays an important role. We cannot look at light as just waves. we must look at light as waves and photons. Same thing for electrons. They are particles, but they're also waves. And so there's going to be wave-like effects. And we know that because for many, many, many decades, they've been observing this kind of phenomena. But let me ask you a challenging question. Suppose that they're getting a bunch of photons, and we are performing here an experiment like two-slit diffraction. What is causing the diffraction of photons? Because one can think actually that a photon is going to go either through this slit or through this slit. So there are different photons, and we are getting some kind of interaction between different photons. And this is what gives interference and diffraction. However, this is not true. And you can prove that in a very simple way. That is, suppose that you decrease the intensity of the photon beam. At a certain point, on the average, you're going to get only one photon at a time in the system. You accumulate these photons using some kind of counter or accumulating device here, and you're getting exactly the same pattern. So with one photon at a time in the system, you're getting the same pattern, which means that basically you cannot have an effect of the interaction between different photons. So the interaction is between a photon and the same photon, a photon with itself. Now, this was realized by Paul Dirac, among other outstanding scientists, many, many years ago. And he was explained in theoretical terms. I don't want to go into the details of this, by what is called quantum electrodynamics, which is the theory of electromagnetic radiation and other quantum objects with advanced theoretical tools. And basically, the theory has been developed in first order phenomena and then higher order phenomena as a function basically of the intensity of the beam that we are talking about. So what we have been seeing for many years are first order quantum electrodynamic effects, which are indeed interaction between each photon and itself. And this has been the situation until now. And now there is something new. There are seeded X-ray free electron lasers, and they are packing enough energy in a small volume and in a short time that the second order effects are no longer invisible. We can start playing with them, and we can start looking at phenomena and techniques in fundamental quantum physics. Keep in mind that we cannot predict everything. Okay, once again, we are packing up too much energy to make predictions reliable. So it is something that may give us surprise in the next year. And I would like to acknowledge the outstanding contribution of my good friend Joe Storr in California, who put these arguments in a very simple way. Okay. I think that I'm over the time, but just a little bit. But let me conclude by, first of all, thanking the organizers of the school for this very nice opportunity. And also I'd like to thank all of you for your attention. Pardon my English, okay? And I hope that you have been able to follow things. Nevertheless, if somebody wants to go deeper into these arguments, this is a list of publications. And as I mentioned to you, I'm going to make available to the organizer a movie with the entire presentation and with a artificial intelligence comment in Spanish. Thank you very much.
Thank you very much, Giorgio. I don't know if we have space for some questions.
Yeah, I'm ready. I know time limitation for.
So, si quiere alguien preguntar, por favor, abra su micrófono, levante la mano o escriba y le preguntamos. Eso, gracias mille. Gracias mille, Alfonso. If not, I would like to thank again Professor Giorgio for your very nice course, very nice lectures. It's really an honor for us to having you here in this first school, and we hope we can have you again next time whenever it happens.
Thank you very much. Thanks a lot.
Giorgio,
The honor was mine.
moltissime grazie Giorgio, speriamo che questa scuola si rifaccia molto presto.
Good. Okay.
Ciao.
Thank you. So long.
Bueno, muchas gracias.
See you tomorrow.
See you tomorrow. Yeah, see you tomorrow in the symposium. Thank you very much. So, mañana, ¿qué? Ahora entonces vamos al descanso para el almuerzo. Y bueno, los esperamos entonces ya se fue Giorgio, así que sus gracias se las pueden dar mañana durante el simposio. Recuerden que mañana el simposio, en la jornada de mañana tenemos una serie de conferencias, de charlas cortas. Una de ellas, la última de la mañana, de hecho, es la de Giorgio. Y en la tarde tenemos el panel en donde se discutirá sobre el futuro, las perspectivas que tendría la iniciativa del ciclotrón para la región del Gran Caribe, desde el punto de vista de lo que podemos hacer como país, como universidad. Entonces, a los que están inscritos de forma presencial, en persona, acá los esperamos en 1 hora y pedacito, o sea, a la 1 de la tarde, para comenzar con la última clase del doctor Alexander Suárez y la última clase del doctor profesor Bernardo Gómez. Entonces, bueno, muchas gracias y ahora nos vemos. Ok. Bueno.
you.